This is video 11 in the series of concrete slabs. We will talk about two-way slabs, and we talked about a specific method of calculating bending moments, and it will deal with the method of Marcus. The bending moment in x direction is calculated with the bending moment according to the method of equal deflection, but with a correction factor nu x. This correction factor is given by this formula, and the value of capital Mx is Q8 squared over 8. Q is the total load of the slab in kilonewton per square meter. And of course, Mxed, the bending moment that you obtain by equal deflection, is of course, if you put it in the general formula, this is the load in the A direction. This is 8 squared divided by alpha A, depending on the three different systems that you got. In the other direction, in the Y direction, it's in fact exactly the same, but with cyclic permutation, you obtain the same formulas. Let's now take a square slab of side A, simply supported on all sides. Then you see Mx is nu Mx equal deflection, and the bending moment obtained by equal deflection is then this formula. We know that omega A equals 5 because it's simply supported, and omega B also simply supported is 5, so this is 5, 5, and A equals B, so we have directly the bending moment for obtained by equal deflection is Q8 squared over 16. Now we calculate the correction factor nu x, which is given by this formula, and we can fill in all the parts of the formula, and we obtain that the correction factor is 7/12 as a value. The mx, of course, the capital Mx is Q8, is this one, Q8 squared over 8. And then finally, the calculated bending moment Mx is Q8 squared over 27.4. You can make this formula more general, and you can write this as the bending moment in x direction is a coefficient in x directions times the Q8 squared. And this coefficient, if you just rearrange the different formulas, you obtain this form, with T equals A over B. Now you can, for instance, use simply supported slab on four sides with the size A and B, and then you see that then you know that alpha A is 8, and because it's Q squared over 8, and omega B in the B direction is 5, and in the A direction is also 5. You fill this in this formula, and you obtain the Kx is a function of T. For a square slab, of course, then T is equal to 1, and then you obtain again Q8 squared over 27.4. This is an easy method to check very quickly with an Excel file the order of magnitude of the expected sagging bending moments in a square isolated slab. What we've seen so far, or what we'll see in the future, is that if you take, for instance, a square slab, simply supported on all sides, then something peculiar is happening. If you use the method of equal deflection, the maximum bending moment equals the total load divided by 16. Total load is Q times A squared. So the equal deflection maximum bending moment is total load divided by 16. If you use an elastic calculation, it will be total load divided by 21. If you use a Medlin solver for final elements, it will be 21.8. If you use another FAM method, finite element method, then it's 22.4. If you use a plastic calculation, it will be 23.5. If you use markers, you have 27.4. And when we will see that in later videos, when we use yield lines, it will be 24. So how is this possible? You calculate the maximum bending moment of a square slab, and you have all kinds of results starting from 16 up to 24. The reason we will see is in fact simple in this sense that equal deflection is an elastic method and yield lines in fact is a plastic method. And for equal deflection, this is a lower bound method and yield lines is an upper bound method. Because we do not have specific formulas, mathematical formulas for calculating slabs, therefore we have to make approximations. And each method has its own approximations with its own advantages and disadvantages. So you must be careful when using the method of calculating the bending moments. Using yield lines means that this is good for strength, but it's not good for serviceability limit state. It's not good for limiting crack widths or for calculating deflection. The equal deflection is a good method for crack width limitation and deflection limitation. So you must take care when you are using one of those methods. And finally, we have one particular solver in a finite element method. Every parameter is fixed for a square slab, and the size of the slab is 10 meters. We calculate the maximum bending moment and the computer says it's 45.86. We use an element mesh of 1 meter. So this means that our bending moment is QL squared over 21.81. Now the same program with the same parameters, exactly the same, but now we put the element size on 0.1 meter. So we have now more elements in it. You recalculate it and you see that you have an other maximum bending moment. So even within the same method, you arrive at different bending moments. So be careful if you calculate bending moments in slabs. It is not so that the maximum bending moment is really fixed. It's really fixed on one figure.